Hello everyone, my name is JUWOOKJANG from Seogang University, Seoul, Korea. The title of my talk today is A Scheme to Reduce MVCC Conflict by Adjusting Block Size in Hyperledger Fabric. My presentation will go in this way. First, I introduce my topic and review some related works. Then I present our scheme and show how we optimized the performance in our scheme. And I'll talk about conclusion. We have two represent most well-known blockchain for smart contract. The first one is Ethereum, which is more public oriented, and the second one is Hyperledger, which is more private and more enterprise oriented. And we want to show, we consider problem of improving data throughput through parallel processing of data, actually parallel processing of transactions. And the following is schematic diagram of Hyperledger consensus, Hyperledger Fabric consensus, but I'll skip this because it will take too much time to give some detail about it. The Ethereum is called world computer because the same program we have here. The same program is run by many different computers connected by peer-to-peer network all over the world. So it is called world computer. In this way, they make sure that the same program is run by many computers to be sure that the same program is run in every node. So that makes it against any hacking or tampering. So just make sure that the same program is run without any possible hacking from bad guys. Smart contract is verified by all laws. Compared with traditional execution, we have an execution file called the program, and it is run on a single computer. So it may be vulnerable to some hack or tampering by some bad guys. But in smart contract, we have many nodes running the same program, so nobody can change the program, and then nobody can tamper the execution, something like that. So we can be very sure that this program is run correctly and without any modification. So that's the good for smart contract. So we can in the open wild internet, we can be sure that some promised contract will be run without any problem. So that's the virtue of the blockchain. Basically, smart contract is something like collection of state changes. Like actually, when we perform transaction, the transaction and the transaction here, right, and the stage before stage and after stage are collected into a block, which is basically a database shared by all participating nodes. So we can be sure that the same stage and the same transactions are preserved in the same way all over the nodes. For example, we have a block here, the before block, and in the data we have a stage, we have a key A, variable A, we have 50 coins, and the variable B has 10 coins. And we have a transaction here. The A sends 50 coins to B. It's a transaction. Then what happened? The DA after stage have 0 coins because it consumed all 50 coins it has, and the B now has 60 coins, more than 50 coins more than before. So we have state changes. So these states, before stage and after stage, and the transaction that caused this stage, this state change, are all into the block. So every node can check and if it is valid or not. So this way the transparency and the immutability are guaranteed all over the nodes. So Ethereum basically generalized this state transition because what is computer? Computer is basically state transition. So we have a state if we have a machine which is capable of state transaction, then we can run any program. So that's the basic idea behind the Ethereum smart contract. So in a fundamental way, we can say that Ethereum can perform any computations as a part of a transaction. In this slide, we show very simple transaction, but in fact, we can perform many complex and multiple transactions in the Ethereum smart contract. So this shows a basic diagram. We have a state, and we have a transaction, and we have an after state. Then we have another transaction, and we have another after stage in this way. So all these transactions and states are stored in the blockchain, shared by all the nodes, so nobody can change it because it is cryptographically protected. In other words, mathematically protected. We see that this one is updated, then it is used in the next transaction. So it's so different, right? So actually, what happens if they use this kind of two instruction? Then in the validation stage, the Hyperledger Fabric discovered this. They know that the same key is updated twice. Then it generates fail error, like two different the same. They are expecting two different versions, but they are used the same version. So this is resulting error, right? So it is so orderer, the final stage orderer labels, it failed because they used the same key in the same block. So approach, this is something like because in Hyperledger they use version number to identify this problem, like so in the Hyperledger they use a version number, right? So we have a key A, which is version number 0, and every transaction shows every transaction is tagged with this version number, because we update B sends something to A, then A will change. But as you can see, the version number of this transaction is for B we have version 0, for A version 0, right? But after this transaction, A should go to the version number 1, like this. For example, here B has $200 and sends $100 to A. Then at the start, at version 0, A has 500. But after this transaction, we have version number 1, in which A version number 1 is now has 600, and B now has 100, because it sent 100 out of 200 to A. So now it is version number A1. So basically, this transaction TX0 has to be performed on the version number 0 of A, version number 0 of B. But transaction 1 is supposed to be version number of 1, version number of A should be version number 1, B should be version number 0. But now, as you can see, because they are in the same block and they use the same version, so this one has a problem, right? Because they should use the version number 1 of A, but instead they use the version number of 0 of 1 A. So this is a problem. So when we have a validated step, they generate errors, because A has. So this is called so-called multi-version concurrency control, because they used the many transactions run together in parallel, so they should clear which versions they use in the same block. So the basic idea is to do not use the same different version in the same block. So we have this here. We have a key Alice version number 3, key Alice version number 2. They cannot be used together. this. For example, we call it dependency. The dependency is defined to how many transactions share the same variable. No dependency, then we have 0. In the highest dependency, we have 300 out of 300 transactions. So this is basically what happens because we have no dependency. Then all 300 block transactions can be run in parallel. But as you know, as you can see, if the dependency increase, then we have more failures, right? So the basic idea behind this is we can reduce the block size if the dependency increase. So this is shows something here. If we have increasing dependency, then the throughput will be diminished. We can find some. We can adapt the block size to the dependency to increase to get optimal transactions per second. That's the basic idea. Or we can change the order. Like for example, TX3 is with the conflict, and the TX4 is not with TX0. Then we can change the order between TX3 and TX4. Then as you can see, we see TX4 is in place of the TX3. So now we have no conflict within this block, so they can be run in parallel and no fail. So that's the basic idea of our scheme. Okay, thank you for your attention, and if you have any questions, you can send me email or some contact, then I can answer your questions. Thank you.